The second type of reaction, this one also you are responsible for the mechanism for. It's the halogenation, which is the addition of the halogen to the alkene in presence of a solvent, which is the carbon tetrachloride. There is a certain stereochemistry for the reaction, and the addition is going to proceed by a trans addition or an anti-addition. Use the term trans whenever you have a cycle. So if you start with an alkene in a cycle, then it's going to be a trans addition. However, if you start with an alkene in a chain, then it's going to be an anti-addition. This is just to tell you that the halogens are going to add opposite with respect to each other. So let's go ahead and have an example in there. So if we have this alkene, let's start with a cycle of 6-membered rings in there. Okay. And this is going to be my alkene, and I am reacting the alkene with the bromine. This is Br2 in there. Now, Br2 is non-polar. However, it's going to produce a certain direction of polarization in there because of the electronegativity of the brimines. So the electrons will not be equally distributed between the brimines. So one of the brimine is going to pull electrons more than the other. And when this happens, you're going to create a fake dipole interaction. And that fake dipole interaction will result in a direction of polarization, which is temporary direction of polarization, causing one bromine to be partial positive and the other one to be partial negative. I need an electrophile to react with my nucleophile. So let's go ahead and highlight our nucleophile in there. And the first step is that the double bond is going to open up. But this is going to happen every time the double bond opens up to an electronegative element. So this bromine is not a hydrogen. This bromine has lone pairs around it. So we need to take those into consideration because I know that electrons also, they make bonds. Every 2 electrons make a bond. So the bromine here is going to add in a special way. And the way that the reaction is going to go, the double bond is going to open up and attack the bromine. However, one of the lone pairs of the bromine is going to come and close the cycle. So you're going to end up having a cyclic brominium ion. And because the double bond is planar, that cyclic brominium ion that you're going to form. So you're forming a bond between this carbon and the bromine and this carbon and the bromine. So because you're forming a cyclic brominium ion, and because this double bond is planar, the cycle that you're going to form is going to be either on the top or on the bottom. So you're going to form the cyclic brominium ion here. So if this bromine is going to be picked up from the top, notice that now bromine lost electrons because the electrons here, they made a bond with this carbon. So to represent this loss of electrons, I'm going to represent it by a plus charge. Every time you make a bond, you break a bond. So the Br minus over here is going to leave. Okay, it's going to be in the solution. And if my cycle over here occupies all the area which is up, what's going to happen to this group over here? This is going to be pushed at the back. So you have to represent it at the back in there. This reaction does not proceed by a carbocation. So there is no carbocation. There is no rearrangement in there because of the bulkiness of the bromine and the lone pairs of the bromine. This is going to open up, pick up the bromine, and the lone pairs are going to create a cycle back. So you're going to form your cyclic brominium ion. So this is called a cyclic brominium ion. Plus your cyclic brominium ion over here is going to form at the back. Since the double bond is planar, so you have both options and you have to consider both options in this case. Here you go. Please don't add carbons. Here I have a carbon and 2 carbons. So go ahead and write the carbon and the 2 carbons in there. Make sure that every single carbon has 1 bond in 2 bonds in plane, 1 bond in front and the other one behind in this case. And these are the 2 options that you are going to end up with. plus, of course, the Br minus that is going to be in the solution. Now, whenever you have a cycle and one of the elements in the cycle is a positive charge, to make the cycle stable, so this plus a charge belongs to the bromine, and the cycle is made up of two carbons and the bromine. So now to make that cycle stable, the charge needs to be distributed between the carbons of the cycle and the electronegative element. Because if that charge is on the electronegative element, this charge means that the bromine lacks electrons, and at the same time, the bromine is an electronegative element. So that is going to decrease the stability of the structure. So what's going to happen here is that the plus charge will be distributed, meaning that the electron deficiency, instead of being just focused on one region of the cycle, it's going to be distributed across every element in the cycle. So now this carbon over here will be partial positive, and this carbon over here will be partial positive. And the reason why this happens, just to make the cycle more stable and the distribution, the charge being distributed instead of being located on just the electronegative element. This happens every time you have a cycle and you have a charge that belongs to one element in the cycle. Then this means that the charge needs to be distributed across every single element in the cycle, specifically if it was a positive charge. So now I'm going to have two types of carbons. And these carbons, they are not carbocations, but they behave like a carbocation. There is no rearrangement in here. But I want to know, because these two carbons are completely different. And I want to know now, because my next step, I know that I am adding my bromine. This is going to be my second step, because the Br minus is going to be in the solution. And this is going to be my next step, where this bromine is going to attack. The rule says that the bromine, the Br minus, is going to attack the most substituted carbon. So that nucleophile here, this nucleophile. So this one here now is my nucleophile. And later on, we're going to study cases of changing that nucleophile into different nucleophiles. So the rule says that the nucleophile is going to attack the most substituted partial positive carbon. Okay, so if I'm comparing between those two carbons in there, this one is going to be the most substituted one. So this means that the bromine is going to come and attack. However, the way that the bromine is going to attack, because see all of this area here, which is up, is occupied. So it doesn't make sense that the bromine comes and attacks from the same side of the cycle. It needs to attack from the opposite side of the cycle so that to break the bond. So the Br minus now is going to come, and now we know that it's going to come and attack this carbon, but see how my arrow is? It's attacking from the opposite side of the cycle. If the cycle is from the top, it's going to attack from the back so that it can break this bond, and this bromine will go to the adjacent carbon. So now my leaving group is going to be the bromine over here, and the bromine is going to come to the adjacent carbon. So my structure now is going to be my first product in there. The Br is going to be at the back because it attacked at the back. And what I did over here is that I pushed the bromine to the front. So now this bromine is going to be on the front. So see, now my addition is going to be a trans addition. This is going to be a trans addition, which is the addition of the bromine to the double bond. Now, if this bromine is at the back, this means that this group over here will be pushed to the front. I don't have any other options. So you have to put it in the front in there. Here you go. So that is going to be your first product, plus the other The other attack is going to be for the other stereoisomer, still on that same carbon in there, because we agreed that this is the carbon which is the most stable carbon because it is the most substituted partial positive carbon, and the nucleophile attacks the most substituted partial positive carbon, and the bond here is going to open up. Notice that when it opens up, this carbon is going to have now the bromine which is at the back. It's going to stay at the back. However, now my nucleophile attacked in front so that the bromine stays at the back. So now my bromine is going to be in front. Again, the nucleophile here cannot attack from the same side of the cycle, so it always needs to attack from the opposite side to break the cycle. This is going to push this group over here to be at the back. Still, I'm going to end up getting my trans addition in this case. So this is going to be a trans addition in this case, and those two, they differ by both chiral centers. I do have here two chiral centers. I have a chiral center here, and I have a chiral center in there. Here you go. If you compare those two together, these differ by both chiral centers, so these two are going to be considered a pair of enantiomers. So let's consider now this example here where the double bond is part of a chain and not a cycle. Let's locate our double bond, and then the chlorine in there. Draw your direction of polarization for the chlorine, showing the partial positive and the partial negative parts of the chlorine. And then the double bond is going to open up, pick up the chlorine, and the lone pairs are going to close in this case. So let's go ahead and consider all the products and then see if the products are going to be the same or not. So the chlorine is going to add either from the top, as we did before. This is going to be a plus charge now. Keep the same stereochemistry of the groups in there. If they are trans, keep them trans. And this is what we do in a chain in there. Plus, the cyclic chlorinium ion can also form at the back. So here I'm forming my cyclic chlorinium ion at the back. Here you go. And there. Now, the Cl minus, of course, is going to leave, and that is going to be in the solution. Now, the chlorine is going to come and attack each one of these carbons, and it doesn't matter which carbon it's going to attack because both, they have the same degree of substitution. Here you go. So this is going to leave, and you are going to end up having your single bond. Here you go. So if it attacks from the front, then your chlorine here is going to be at the back. Plus, it can also attack. Let's do that same carbon over there at the back so that it opens, and you're going to end up having your group in front. So it's going to attack at the back so that the chlorine over here is going to be in front. Okay, now notice what I have in here. I do have two chiral centers, yes. This is a chiral center in there, and this is a chiral center. This is a chiral center in there, and this is a chiral center. But these two are the same molecule in here. Why they are the same molecule? Because I can simply do a simple rotation around the carbon single bond carbon in here. And if I do a simple rotation around this carbon, then this chlorine is going to be behind. So I'm going to end up having a meso compound in this case. So I'm going to end up having a chlorine which is behind here, and the chlorine which is behind in there. So this is going to be a simple meso compound. So this is why this meso compound, these two are not enantiomers. These two are going to be the same because if I rotate one, I'm going to simply go ahead and get the other one. And my product is going to be just one product in there. You don't have to show both of them because these two are going to be the same. and add water to the chlorine instead of using the chlorine alone. Now, earlier, we used just the chlorine, and the chlorine was the source of both the electrophile and the nucleophile. So you created your cyclic chlorinium ion in there, and then the halogen or the nucleophile attacked. That nucleophile was the result of the leaving group of the chlorine. So that nucleophile attacked the most substituted carbocation-like or partial positive carbon. So now this nucleophile, I want to change it and make it water. The reaction is going to proceed exactly the same. So the first step, I am reacting the alkene with the chlorine. So you're going to form the cyclic chlorinium ion in this case, as usual. So the double bond is going to open up, pick up the chlorine, assuming that this one is partial positive, this one is partial negative. And the lone pairs are going to close, and you're going to form the cyclic chlorinium ion. And the cycle is going to be either formed from the top, or it's going to be at the back. It's exactly the same thing. So I'm going to have my chlorine in here, and the cycle is going to be formed at the top. Don't forget your plus a charge, plus the cycle is going to be formed at the back. Okay, don't forget any of your groups in there. Now, once you form your cycle, of course, the chlorine is going to leave and it's going to be in the solution. So, of course, you're going to end up having plus the Cl minus in the solution. However, we are looking at the concentration because I know that the Cl minus is a good nucleophile, but at the same time, if I am comparing the concentration of the Cl, which is found in the solution, versus the concentration of the water that I have, I would see that the concentration of the water is going to be more than that of the chlorine. So this makes the water attacking faster than the chlorine. So the water here is going to be my nucleophile because it is present in a higher concentration. In a higher concentration than the chlorine. So this is why the water now is going to attack in the next step and not the chlorine. It's going to proceed exactly as the chlorine did. So we're going to add the water in this case now here across every single carbon. So every single carbon here will be partial positive, and the attack of the nucleophile is going to be towards the most substituted partial positive carbon. So the most substituted partial positive carbon in this one, because this one is connected to 2 carbons versus this one is connected to just 1 carbon. So this is going to be the most substituted for both. Okay, so now the water is going to attack. So the water is going to come and attack, and it's always going to attack from the opposite side of the cycle. So we're still doing the same stereochemistry in there, which is the trans addition. Every time you're adding a halogen in there, the halogen is going to create a cyclic halonium ion, and that cyclic halonium ion will occupy all the area, whether up or down. So if any nucleophile want to attack, no matter what that nucleophile is, it's going to come from the opposite side of the cycle just to open the cycle up. Head and open the cycle up in there. And this one also, it's going to do exactly the same thing. It's going to attack from the top so that it opens the cycle from the back. So you're going to end up forming 2 products. Water is going to attack at the back. So go ahead and draw water. Now, every time you are using, notice that here my nucleophile is neutral. And if you remember from the chapter before, every time you are using a neutral nucleophile, you need to use that nucleophile either twice, or you need to have a base in the solution, any base to pick that extra hydrogen that you make. That chlorine is going to be at the top in there. Plus, your second product in there. Again, you don't have any carbocation in here. There is no carbocation rearrangement. So water is going to attack from the top, and the chlorine is going to be at the back. The addition has to be a trans addition every single time. So here you are creating actually two chiral centers in this case, but I am not done yet because I still have this positive charge product, and all my products, they need to be neutral. This is the rule. So I need to use any base in the solution, any base, to pick that extra hydrogen in there. I can use water again. So water here is going to act as a base. Okay, just for simplicity, you can go ahead and do base with two lone pairs in there, and that base, which is the water. Okay, so that base is the oxygen in there. Any base with lone pairs can do the job. I would stay away from the Cl minus because the Cl minus is not a strong base. Cl minus is a strong nucleophile, but it is a weak base in there. So I will not use it in order to pick that extra hydrogen because we want to avoid the formation of HCl in there. So water is a better choice in order to come and pick up that extra hydrogen by a Lewis acid or a Bronsted acid, Bronsted and Lowry acid base reaction. So the water here is going to come, take the hydrogen and form a lone pair on the oxygen, or it can come over here, take this hydrogen and form a lone pair on the oxygen, so that your product now is going to be the neutral product. So you're going to end up having your chlorine, your OH over here, plus, so water is always going to add in a form of an OH. This is going to be your chlorine over there and your OH here. So notice, what did I form? These two are going to be what? These two are going to be enantiomers, and they are enantiomers because they differ by both chiral centers. So I have two chiral centers in there. Do the configuration for both chiral centers, and they are going to be different configurations. So these are going to be a pair of enantiomers. I can change this nucleophile, and I can make it any type of nucleophile. Like, for example, I can make it an alcohol or ammonia or any of the derivatives of ammonia. If I have a cycle, let's say if I have my double bond in here, and I am reacting this with chlorine in presence of methanol. Okay, so the idea is exactly the same. You are going to first add the chlorine and then add the alcohol, because the alcohol will be found in a higher concentration than that of the chlorine. So this is going to be our partial positive, and the double bond is going to open up, is going to pick up the chlorine, and the lone pairs are going to close. So you're going to be forming the cyclic chlorinium ion in this case. And the cyclic chlorinium ion, let's go ahead and make a CH3 over here. Here you go. So you're going to form your cyclic chlorinium ion, and the cyclic chlorinium ion can either be on the top, okay, plus it can be at the back. Okay, so now we're going to go ahead and use the methanol to be our nucleophile, because we agreed that methanol is found in a higher concentration than that of the Cl minus. Of course, the Cl minus is going to leave. So that now the methanol is going to come and attack the most substituted carbocation-like or partial positive charged carbon. This is partial positive and this is partial positive. And the most substituted partial positive charged carbon is this one. This is going to be the most substituted because this carbon is connected to 2 carbons over here. However, this carbon in there is connected to just 1 carbon in there. Even though there is a branch, but this is the branch of the cycle in there that has more carbons than this one. So this is why this is going to be more substituted, and methanol is going to come and it's going to attack in there, and it's going to attack from the opposite side of the cycle. So if the cycle is up, then it's going to attack from the back. And if the cycle is at the back, then it's going to attack from the front. But it's going to attack on that same carbon because it is the most substituted carbon. So now my product is going to be, here you go. I have my methanol in there, and the methanol is going to be at the back. I made a bond between the oxygen, the hydrogen. Please draw all the methanol in there. This is going to be my CH3 plus a charge. And then my chlorine here is going to be in front. Plus, I have my second product in there. I have my methanol at the back. Actually, the methanol needs to be in front. So the methanol is in front there. And the chlorine now is at the back. This is the CH3. And the chlorine is at the back. Then you're going to go ahead and use a base. And we agreed that the base is going to be any sort of lone pair in the solution. So it can be another mole of methanol. So I can use another mole of methanol, but for simplicity, I can also use like just a base with a lone pair. Okay, that means that another mole of methanol, since this is the only thing that I have in there, and I want to stay away from the chlorine. I don't want to make an HCl. So that base is going to come, and it's going to attack the extra hydrogen here and form a lone pair on the oxygen, or it's going to come over here and take this hydrogen and form a lone pair on the oxygen. So you are going to end up getting 2 products in this case, and these are going to be your neutral products. You always stop your reaction whenever your final product is a neutral product that has no charge. So as you can see here, this is a trans addition. You have to show that it's a trans addition. And now I am adding the OCH3, and it is a trans to the halogen plus my second product in there. I cannot draw a plane of symmetry in here, so I don't have meso in this case. So these two definitely are going to be a pair of enantiomers. So this is going to be a chlorine, and these two are going to be a pair of enantiomers in this case. I have 2 chiral centers. I have a chiral center here and a chiral center there. And these 2 chiral centers are different for both. So these are my 2 optically active products. And they are optically active again because they are coming from an optically active reactant. So let's say, for example, I change now my nucleophile and make it ammonia, make it NH3, or any of the derivatives of ammonia, like RNH2, for example. Okay. Then in this case, let's say if I am adding the NH3, the NH3 is going to add in place of the OCA of the methanol. So I'm going to end up having NH3 in there. Nitrogen will be positive. I'm going to use another NH3 to pull out the extra hydrogen of the NH3, and I'm going to end up with an NH2 in there. Again, they have to be trans. Every time I form a cyclic chlorinium, brominium, or any halonium ion, the attack always of the nucleophile needs to be on the opposite side of the cycle.